This chapter focuses on the tools people use and the expertise that makes those tools effective. The main idea is that good results usually come from combining the right method with real skill. Domain expertise sets the standard for every edge AI decision that follows. The real question is whether the team understands the problem well enough to build something worth deploying. Before models, sensors, or deployment plans, the team needs proof that the problem is real, important, and workable in its actual setting. That gate protects the project from elegant solutions to the wrong problem. A strong model still fails if the team misunderstands the environment it will live in. Domain expertise anchors the work in reality, so the product solves a real need instead of chasing a technical idea. That kind of knowledge is practical, not theoretical. It tells you what people actually do, where the process breaks, and whether automation would help or just create a different kind of problem. The first job is to validate the problem with discipline. If the pain point is vague, rare, unsafe, or not worth solving, engineering effort should not start yet. Good validation starts with plain questions about who feels the pain, how often it happens, and what makes it harder than it looks. Those answers tell the team whether the work is meaningful or just technically interesting. Once the problem is clear, the limiting factors become visible too. Noise, latency, rarity, and ambiguity are not abstract concerns. They're the reasons a project succeeds, stalls, or needs to change direction. A promising idea can collapse when a field expert reveals the true signal, the real maintenance burden, or the environmental drift in the data. That kind of correction is valuable because it prevents the team from building around a mistaken assumption. Customer feedback matters, but it does not replace deep knowledge of the domain. The person who buys a system is not always the person who understands its risks, its constraints, or its hidden consequences. Customers can tell you what they want and what frustrates them. They cannot always tell you whether the idea is safe, compliant, or aligned with the actual workflow that governs the problem. That mismatch matters in Edge AI because systems often affect people who never signed a purchase order. If a design depends on exposing unqualified people to danger, it is not a product decision anymore. It is negligence. Domain knowledge works best when it shapes decisions every day, not only during occasional reviews. It should influence requirements, data interpretation, edge cases, and the final call on whether the result is good enough to ship. The strongest setup spreads that knowledge across the people doing the work. One advisor cannot catch everything, but a team that shares the domain perspective is much harder to mislead. That distribution can look different depending on the size of the organization. The important point is that technical people, leaders, and outside experts all understand the operating reality well enough to recognize risk. A real field conversation usually narrows the design in useful ways. It reveals what outputs matter, what maintenance is acceptable, and what kind of system would actually help the people on the ground. When no qualified expert is available, caution has to win. The responsible move is to pause, learn the domain, or bring in the right partner before committing to build. Some concepts deserve more field study before they deserve engineering time. If the team cannot reach that knowledge, the project should slow down rather than pretend uncertainty is harmless. That pause is not pessimism. It is a safeguard. Teams that build too early often automate the wrong thing, and then the system fails exactly where the domain knowledge was missing. When hiring, the goal is not a perfect title match. The goal is someone who can recognize the real problem, work with technical specialists, and help the team make grounded decisions. A candidate with strong operational knowledge and enough technical fluency can be more useful than a glossy resume. What matters most is whether they can validate the problem and bridge the gap between field reality and the technical stack. For an individual builder, hands-on practice can raise technical confidence and make the hardware side less intimidating. Even so, learning the stack is only half the job. The other half is understanding the real environment well enough to avoid building the wrong system. Edge AI works when the domain comes first and the tools follow. Models and deployment can support a good decision, but they cannot rescue a project that started with weak assumptions. Domain expertise decides whether an edge AI idea belongs in the real world or only on paper. The focus here is how to use evidence from actual work, actual constraints, and actual judgment to shape the product correctly. A strong product starts with evidence from the field, not with a feature wish list. The point is to understand the problem well enough that the technical work lands on the right target. The first useful evidence is the setting itself. Who is working, what they're doing, and what makes the situation difficult. Expert judgment matters because it tells you whether the problem is worth solving before you spend time building for it. Technical teams can improve a proposal very efficiently once the target is set, but they often miss when the target is wrong. Someone who lives inside the workflow can spot a bad assumption immediately because they know what actually matters in practice. The first conversation should be concrete and unsentimental. Good questions force the team to separate real pain from interesting ideas, and they expose whether the problem is defined clearly enough to work on. If people already invent workarounds, that usually means the pain is real. The size of that pain tells you whether the problem deserves attention or is just an inconvenience. Frequency and context matter because a problem that appears rarely may not justify a system, while a daily problem in a critical setting can be worth serious effort. You want to know exactly whose work is affected and when the damage happens. That question measures consequences. If the cost of doing nothing is low, the project may not be urgent. If the cost is safety, time, or money, the problem becomes much more meaningful. Not every decision belongs in software. Some judgments are too risky, too ambiguous, or too sensitive to hand over to a model, and a domain expert helps draw that boundary early. A real outcome has to work where the task actually happens. That means the result must fit the environment, the workflow, and the people who have to act on it. This question is a reality check. Constraints such as noise, cost, safety, latency, or power can kill an idea even when the concept sounds good in theory. Those questions test both demand and technical reality at the same time. A domain expert can tell you whether the signal can be observed, whether the environment is too messy, and whether the machine learning approach survives the actual constraints. A concrete example makes the judgment clearer. The point is not just to hear opinions, but to watch how an expert reshapes the problem once the team describes it in the language of the field. A startup may arrive with a polished demo and a broad promise, but a real facilities manager immediately narrows the scope. Good domain judgment does not kill the idea. It turns the idea into something specific enough to evaluate honestly. The useful problem is not every possible hazard. It is the subset that can be seen reliably, happens often enough to matter, and leads to a response in time. The expert also watches for false alarms, missed cases, and the people who may be affected beyond the paying customer. That is the practical value of expert input before development starts. A good expert helps define a problem that can actually be built, checked, and trusted in the field. Expert judgment cannot be treated like a one-time review. It has to sit inside the team because product decisions keep changing as data, deployment, and operational trade-offs become visible. The questions keep coming throughout the project. What to collect, what matters, what failure costs, and what trade-offs are acceptable. If the expert arrives only at the end, the team may already have made choices that are expensive to undo. A useful team puts the domain expert at the center of product definition, with engineers translating that knowledge into model and device choices. Leadership then reinforces the same judgment, so the domain knowledge shapes hiring, budget, roadmap, and launch criteria. The strongest teams do not search for one person who knows everything. They start with the problem, bring in subject matter knowledge, and then add the technical skills needed to execute without losing sight of the field. There is also a line that should not be crossed casually. When qualified expertise is missing, the responsible choice is to pause rather than guess, because the wrong kind of confidence can create bad products and real harm. Direct customers can help, but they are not a substitute for informed validation. The team still needs someone who can judge feasibility, safety, workflow fit, and downstream impact with real authority. That boundary matters even more when the system operates in public. A product can sell well and still be careless if it ignores the people who live with its outputs. So the team has to ask who is affected and what harm might follow. For a solo developer, the path is similar but more personal. Hardware practice builds intuition for power, interfaces, debugging, and deployment friction, yet it never replaces real knowledge of the target domain. The final rule is simple to state and hard to ignore. Before building, confirm that the problem is real, that someone qualified understands it, and that the team has the judgment to make the right trade-offs. Domain expertise is not a side note to the product. It is part of the product itself. When that judgment is absent, the right move is to stop and find it before moving forward. Diversity matters because it helps a team see risks that technical skill alone can miss, especially when the product will affect real people in real settings. A team can be highly capable and still build the wrong thing if everyone shares the same assumptions. Domain expertise tells you what is feasible, but diversity helps reveal what that expertise may overlook. The point is not to replace expertise, it is to complement it. People with different lived experiences and responsibilities notice different failure modes, and that changes the standard for what the product should solve. A useful way to think about diversity is to separate it into four perspectives. Each one catches a different kind of blind spot. These dimensions give structure to the idea, so the team can ask where its missing perspective actually comes from instead of treating diversity as a vague ideal. The first dimension is diversity inside the team itself. That includes background, training, age, caregiving load, disability, culture, and work history. These differences matter because they change what a person immediately questions. One teammate may think about family schedules, while another may spot that an alert works in theory but fails in daily life because of sight, hearing, dexterity, or attention limits. The second dimension reaches beyond the team itself. It brings in customers, affected communities, field operators, reviewers, and advisors. That matters because a product often creates effects for people who never buy it. In Edge AI, neighbors, visitors, maintenance crews, and downstream decision makers may all live with the consequences. The third dimension is role diversity inside the organization. Engineering, operations, support, product, deployment, compliance, and management all see different failure modes. A model builder may focus on accuracy, while someone in operations may care more about mounting, resetting, or servicing the device when conditions are bad. Those are different tests of whether the product is actually ready. The fourth dimension is worldview, the mental models and risk priorities people bring to the same problem. Two people can hold the same job title and still disagree about what matters most. One may focus on latency, another on false alarms, trust, or whether automation should ever operate alone in a high-stakes setting. In practice, these perspectives are most valuable when they expose problems before deployment. A field technician may understand maintenance in bad weather. A community member may know how alerts should be presented, and a caregiver on the team may question whether the schedule is realistic for people with limited flexibility. A person's own experience can reveal a real problem, but it does not automatically make them the specialist for that domain. The right response is to treat that experience as a warning signal and then bring in the needed expert. Diversity only helps when people can actually voice concerns and expect to be heard. That depends on psychological safety. People need room to question a plan, admit uncertainty, or challenge a decision without being mocked or sidelined. Without that, a team may look diverse on paper but still function like a closed room. Leaders have to make dissent usable by asking for uncomfortable views early. The best time to hear, "This is the wrong thing to optimize," is before the architecture and the habits around are already fixed. When a needed perspective is missing, the gap should be filled intentionally. Feedback sessions, focus groups, and advisory boards can bring in the people who live with the consequences, especially when the product affects homes, schools, clinics, or public spaces. More perspectives improve judgment, but they can also slow consensus. The useful habit is to record the disagreement clearly instead of pretending it never existed. A short decision log is enough to capture what was chosen, what else was considered, and what concerns were raised. That makes later review much easier, especially when the issue touches safety, accessibility, or deployment burden. That record prevents the team from forgetting why a choice was made when pressure returns later. It also proves that disagreement was handled as part of the process, not treated as noise. That same habit is a strong signal in hiring. Good practitioners can work with domain experts, notice missing perspectives, and participate constructively with users, operators, and outside reviewers. The practical result is a team that is technically credible and socially resilient. Diversity becomes an engineering advantage when it is broad in perspective, honest about its gaps, and structured to hear dissent before deployment. Diversity matters here because edge AI fails when a team confuses technical skill with complete understanding. The focus is on how different perspectives improve product quality, reduce risk, and expose problems before they reach real users. A strong team can still miss what ordinary life looks like outside the lab. In Edge AI, the same system may have to work in homes, clinics, factories, or public spaces, so broader experience helps define what safe and usable actually mean. That matters because the first specification is often incomplete. Someone with parenting, accessibility, or fieldwork experience will catch assumptions that a narrow team treats as normal, and those assumptions can decide whether the product survives contact with reality. These four lenses help separate different sources of blind spots. Each one adds a different kind of pressure on the design, and each one helps the team ask better questions. It helps to break the idea into a few overlapping layers. That makes it easier to see where the team is strong, where it is narrow, and where outside input is needed. The people on the team notice different failure modes because they live different lives. One person with children may question constant attention demands, and that can lead to changes like delayed alerts, clearer escalation, or safer fallback behavior. Input from outside the core team is essential, but it should not be confused with final engineering judgment. Lived experience can reveal a real accessibility problem, while specialists help turn that problem into a solid solution. Different roles inside the company see different consequences. If only the buying side is heard, the team misses the people who will live with the product after launch, including workers, visitors, family members, and maintenance staff. This layer is harder to measure, but it often exposes the deepest mistakes. One person may optimize for convenience, while another cares more about control, privacy, or fail-safe behavior. And a uniform team can easily optimize the wrong goal. No single person can stand in for an entire category of users. The value of diversity is that it multiplies the questions the team asks, not that it turns one colleague into a spokesperson for everyone else. A good mix of perspectives only helps when the organization has a process that can hear them. That means making space for disagreement, uncertainty, and awkward questions before the design hardens. People need to be able to challenge assumptions without being punished for it. If speed is rewarded and dissent is not, the team may keep diversity on paper while losing its value in the room. That safety needs structure behind it. Early prototype reviews, pilot feedback, and outside advisors can surface practical concerns before the product becomes difficult to change. When the affected community is unfamiliar or the consequences of a wrong assumption are serious, consultation becomes the right tool. That matters especially for non-users in shared spaces, because they are easy to overlook and often feel the impact first. Small teams can cover several roles, but role coverage is not the same as perspective coverage. Even when one person wears multiple hats, the team still needs outside input for the gaps it cannot fill internally. The practical payoff shows up in the problems a benchmark never reveals. Diversity catches usability, accessibility, and environmental issues before they turn into launch failures. Technical scores do not tell you whether people can actually live with the system. Broader perspective exposes family constraints, work constraints, and public space constraints that only appear once the device leaves the lab. That wider view saves time later because it catches weak assumptions early. It also stands out in hiring, since strong contributors can work across disciplines, listen well, and know when to bring in expertise they do not have themselves. More perspectives usually means slower agreement, and that cost is real. The useful response is to document what was decided, what concerns remained, and when the team should revisit the choice so disagreement stays productive instead of silent. That is the working rule to carry forward. Do not assume the team already understands everyone affected by the product, because in Edge AI, that assumption is usually the first thing that breaks. Stakeholders are the people or groups that can affect a project or be affected by it. That matters because every important decision changes for someone, and good analysis starts by identifying who those people are. A stakeholder is anyone affected by the system, not just the person who buys it or uses it directly. That broader view matters because edge AI changes real environments, so the people around the system can matter just as much as the person at the controls. The circle has to widen beyond the customer. A project can succeed for the buyer and still create work, friction, or risk for operators, internal teams, or people who feel the effects indirectly. Edge AI sits close to physical spaces, so its impact spreads into routines and surroundings. A device can change how a factory is maintained, how shoppers behave, or how passersby experience a public place, even if they never intended to use it. That makes the categories useful. Direct stakeholders interact with the system on purpose. Indirect stakeholders feel the effects without being the target audience. And internal stakeholders carry the burden of operating and supporting it. A brittle alert or awkward maintenance flow can hurt a team long after the model itself looks fine. A system is only useful if it fits the real problem and the real workflow. It is only safe if it does not exclude, confuse, burden, or expose people in ways the team failed to consider. Public deployments make that especially clear. Even accurate models can feel intrusive or unwelcome if they are noisy, poorly signposted, or hard to understand, because non-customers still live with the experience of the device. Stakeholders should stay involved from the first idea through retirement. They help define the problem, expose missing cases, reveal trade-offs, and describe what actually happens once the system leaves the lab and enters the field. Mapping groups by impact helps the team see who benefits, who pays the cost, and who might be overlooked. That simple map leads to better questions and prevents the loudest voice from becoming the only voice. This is part of good team building as well. Employers value people who can connect technical choices to operational reality and human consequence, because the best deployment answer is the one that fits the whole system of affected people. That habit carries into the next idea. Involvement matters, not just identification. Good edge AI work keeps checking back with the people affected because their needs change as the system moves from sketch to launch to shutdown. Stakeholder analysis matters because edge AI affects more people than the buyer or operator alone. The goal here is to identify who is affected, how the effects spread, and why that changes the design. A project can have one purchaser and many more affected people. With Edge AI, the system sits in a real place, so its effects spill into the surrounding environment and reach people who never signed up for it. The first task is to name everyone who may be affected, directly or indirectly. Once that boundary expands, the team starts seeing the real social footprint of the system. Direct stakeholders use, run, build, or support the system. Indirect stakeholders may never touch it, but they still feel its impact through shared space, shared risk, or change behavior around them. That matters because Edge AI changes physical settings, not just screens. A device can alter who gets noticed, how a room feels, or who has to adapt, and those effects are easy to miss if the buyer is the only voice heard. Public-facing deployments need extra care because the people affected are not limited to customers. The broader the setting, the more important it becomes to account for non-users and bystanders. A smart camera or building sensor may be bought by one organization and experienced by many people nearby. Those people can be helped, monitored, excluded, or harmed, so they belong in the stakeholder set. A system can satisfy the customer and still fail the environment it enters. Once the team counts the wider impact, it can change placement, sensing range, retention, or even the use case itself before harm becomes normal. That early change is the real value. It pushes requirements upstream before the design hardens and the cost of correction becomes much higher. Stakeholder needs do not belong only at launch. They influence what gets built, how it gets deployed, and how it should be retired. At the start, stakeholder input helps decide whether the problem is worth solving at all. Later, it sets design boundaries, deployment rules, and end-of-life plans for deletion, recovery, and shutdown. A device keeps shaping people's experience after launch, so a one-time review is not enough. Missed harms usually surface late, when changing the system is expensive and trust has already started to erode. The practical question is how to find the people a normal product discussion skips. A stakeholder map gives the team a disciplined way to look beyond the obvious users. Stakeholder mapping organizes affected groups by proximity and kind of impact, then records what each group needs or fears. It does not need to be elaborate. It just needs to happen early and be owned by someone on the team. Good mapping forces sharper questions. Who is there when the system runs? Who sees its outputs without choosing to? And who carries the maintenance or explanation burden? Those answers should shape the architecture before it becomes difficult to change. A concrete example makes the trade-offs easier to see. Once the setting is public, the number of stakeholders grows quickly. A building entrance sensor may serve the property owner's goal, but it also affects tenants, visitors, workers, and people passing by. If the team listens only to the buyer, it may create nuisance alerts or a sense of surveillance. If it includes nearby residents, it can choose rules and placement that reduce spillover. That is the important shift. Stakeholder analysis changes what the product becomes, not just how it is described. This work belongs in the core team because it turns human consequences into engineering input. Someone has to translate real-world impact into decisions the product and technical teams can act on. A mature team needs someone with stakeholder, product, design, or operation skill to cover that translation role. The title matters less than the function, keeping the system centered on the people it affects, not only the people who requested it. That habit improves both technical quality and social trust. It helps the team avoid building something that works on paper but fails in the world where people actually meet it. The final test is simple. The product should fit the full set of people and places it touches, not just the person who asked for it. That question keeps the team honest about whether the system should exist in this form at all. Edge AI works best when every responsibility is visible. Who defines the problem, who plans the work, who builds the model and device, and who keeps it reliable after launch. Clear roles prevent elegant ideas from failing because of confusion, missing expertise, or vague ownership. The work reaches from model design to deployment in the field, so a good idea can still fail if the team starts with the wrong assumptions. The first question is always who owns the problem definition, the success criteria, the build, and the long-term reliability. Small teams often combine jobs in one person, and that is normal. What matters is that the responsibilities still exist in the plan, even when one founder or engineer is carrying more than one hat. A useful team model is functional, not bureaucratic. The names of the roles can vary, but the work still has the same needs. Understand the domain, plan the execution, build the algorithm, integrate the product, and support the system around it. The first responsibility is to frame the right problem, because a technically strong solution is useless if it solves the wrong need. Domain knowledge tells the team what is measurable, what is plausible, and what failure looks like in practice. A soil scientist, a facilities manager, and a clinician all see different constraints in the same broad project. That expertise protects the team from building the wrong detector or chasing a metric that does not reflect real use. Blind spots also matter here, especially when a system affects people who did not ask for it. If the data is unrepresentative or the design creates unfair harm, that is a signal to redesign the project, not patch it later. Planning turns the broad goal into ordered work. Someone has to sequence decisions, manage trade-offs, and keep people aligned even when they come from different technical backgrounds. That role may sit with a product manager, technical lead, project manager, or founder. The job is not to micromanage every technical choice. It is to make sure the right choices happen in the right order with the right input. A vibration monitoring device is a good example. One person can gather requirements and set milestones, while the technical lead and domain expert decide what signals to use, how the device should sample, and what conditions the prototype must survive. That same coordination becomes even more important across several business units. Without it, one team saves money while another adds support burden, and the company ends up with disconnected efforts instead of one coherent capability. The next set of roles turns the idea into a working system. The model, the device, the backend, and the support functions all have to fit together because a strong notebook result can still fail on real hardware. Algorithm work produces the model or signal pipeline, and product engineering makes it run in the real world. If memory, power, latency, or sensor placement are ignored, the system may look good in development and fail on device. A wearable motion classifier shows the handoff clearly. Wrist data and pocket data are different, so both the algorithm designer and the hardware engineer need to agree on placement, timing, memory, and retraining needs as the prototype changes. Many edge systems still need APIs, logs, dashboards, or update pipelines even when inference happens on the device. Embedded work and back-end work cannot be treated as separate afterthoughts when a product depends on connectivity or fleet management. Supporting services make the whole system safer to ship. Versioning, reproducibility, security, and robustness testing matter because edge devices live in messy real conditions, not in ideal lab environments. A small team shows how these roles can overlap without disappearing. The important part is still the same. Every responsibility has an owner, even when one person is carrying more than one function. For a smart shelf sensor, one person can bring retail knowledge, another can handle the technical build, and a third can coordinate pilots, data collection, and labeling. That mix covers the product from field reality to prototype behavior. During prototyping, the same person may also help with dashboards or back-end glue because the team is still small. The danger is pretending overlap means no expertise is needed. Someone still has to own model behavior, device behavior, field constraints, and reliability. Hiring for edge AI usually means combining adjacent strengths, not searching for one person who can do everything. A capable team is built by assembling model, embedded, back-end, and domain knowledge across people. A strong hire might come from machine learning, DSP, embedded systems, software engineering, or deep domain experience. What matters is whether the group can carry the work from problem definition all the way to on-device execution. The better approach is to identify the missing functions and build the team around them. For a learner, the same rule applies. Understand how the pieces fit before worrying about the tools that implement them. When roles are explicit, coordination gets easier and handoffs are cleaner. Even in a small team where people wear multiple hats, everyone still knows which responsibility they own and where the boundaries sit. The main question here is how the work gets divided so the product is actually buildable, safe, and maintainable. The role list matters because it exposes the responsibilities the system really needs, not because every title has to become a separate hire. A role map only helps if it reflects the real job in front of the team. In Edge AI, that means asking who understands the domain, who builds the model, who owns the device, and who keeps the system trustworthy over time. A team can build something that looks good in a lab and still miss the actual operating conditions. The domain expert points to the constraints that matter most, like lighting, cost of false alarms, or which defects are truly worth catching. Ethics enters early because the system often affects more people than the buyer alone. Once a product can monitor, classify, or exclude someone, the team has to treat those people as stakeholders and decide which harms are unacceptable. These responsibilities split in different ways. Product work decides value and scope. Project work keeps the schedule and dependencies under control, and program work aligns multiple related efforts. On a small team, one person may carry all three at once. A small team often has to overlap roles to move quickly. The useful test is not whether the org chart is tidy, but whether the important decisions still have an owner. A startup example makes this concrete. One person can shape the feature set and coordinate data collection, while another builds the first algorithm and cleans the samples, and a third handles embedded software and backend integration. That overlap is normal when the product is still being defined. The boundaries between disciplines are porous, so the algorithm is rarely isolated from the rest of the stack. Signal processing, feature engineering, model design, and device limits all shape what counts as a usable solution. Hardware decisions can change what software is even possible. The constraints of the device set the ceiling for model size, latency, power use, and how much signal quality the algorithm can recover. Sensor placement, battery life, memory, heat, and enclosure design all affect the model. A more accurate network may still fail if it is too slow, too large, or fed a weak signal. So the hardware and algorithm teams have to agree on what good enough means. That trade-off shows up fast in wearables and fixed sensors. The team has to balance model quality against space, battery, comfort, and maintenance, or the device works on paper but not in the field. Once the device has to report events, support remote review, or manage fleets, back-end software becomes part of the job. The product needs storage, diagnostics, updates, and trust at scale, not just a model running locally. As the prototype hardens, support roles matter more explicitly. Model operations, security, and quality assurance keep the system version protected and predictable, and each one needs an owner, even if the same person covers several of them early on. Specialized edge AI experience can be rare, so strong teams look for people who can cross boundaries. Generalists who learn quickly, communicate well, and know their limits are often more useful than someone who only fits a narrow title. The role list is valuable because it reveals the work that must happen. Success comes from making sure the right people own the domain, the scope, the model, the device, the security, and the validation before users encounter the system. The practical rule is simple. Organize around the work, not the title. Let responsibilities overlap when the team is small, and add specialized ownership as the product becomes more complex and the risk grows. Titles can help, but they should never drive the design of the team by themselves. The right structure grows from the actual responsibilities the product needs, and from how those responsibilities change as the system matures. Edge AI hiring works differently because direct experience is rare. The main question is not who has done every part before, but who can cover the important pieces and learn the rest quickly. A perfect resume can be a trap in this field. It is usually more effective to find people with nearby experience, strong learning habits, and the ability to take responsibility for the work that matters most. The search usually splits into two different kinds of expertise. One side shapes the model, and the other side gets it running reliably on the device. Algorithm work is about building something useful, efficient, and trained on realistic data. Embedded work is about making that model survive in a real product under tight memory, timing, and reliability limits. Those two skill sets overlap, but they are not the same job. A great model builder may still need support with firmware and integration, while a strong embedded engineer may need help understanding model formats and ML failure modes. The choice between applied and academic ML matters because the work may need either delivery instincts or deeper research strength. The right hire depends on whether the problem is mostly about shipping a solution or inventing a new method. Applied ML people are often strong early hires because they frame problems well and stay close to the data the system will actually see. They tend to ask about available signals, important failures, and what success looks like outside the notebook. Research backgrounds can be valuable when the project needs novel modeling. The gap is usually in product workflow, release discipline, and the willingness to trade some elegance for robustness on hardware. That difference is a hiring signal, not a judgment. If the task is invention, research depth helps. If the task is deployment, practical delivery instincts often matter more. Sensor-heavy edge systems often need people who understand signals before they ever reach a model. That makes DSP experience a very useful bridge into this work. A lot of ML engineers have not worked much with raw sensor streams, even though edge AI often starts there. Those signals can be noisy, uneven, sparse, or oversampled, so the hiring pool becomes more interesting when you look at people who already think in signal terms. DSP engineers already work with windows, filters, transforms, and feature pipelines. Those habits carry over naturally when the input is audio, vibration, inertial data, radar, or any other streaming signal. Embedded engineers sit where the model meets the machine, so their role goes far beyond loading code onto a board. They need enough system awareness to keep the product stable when the model is under real constraints. They often have to integrate runtimes, track down latency or memory problems, convert models into usable formats, and make sure the device behaves predictably in the field. That combination is what turns a demo into something shippable. An embedded engineer does not need research-level ML knowledge, but they do need enough literacy to spot when a conversion changed behavior or when a model that looked fine on desktop starts failing on device. Without that, debugging becomes guesswork. Sometimes the best solution is a simpler classifier or a hand-engineered feature pipeline that fits the power and hardware budget. In those cases, adaptability matters more than whether the role sounds ML native. A small team often has to assemble capability from multiple adjacent hires instead of waiting for one rare specialist. The useful question is how those people cover the whole path from signal to model to device. A practical starting team might include an applied ML practitioner, a DS-oriented engineer, and an embedded engineer. Each person brings a different strength: problem framing, signal understanding, and device integration. That setup is not a compromise in a bad sense. It is often the fastest way to get real progress, because each hire protects a different part of the system, and together they form a workable core. A research-heavy candidate can still be the right pick if the team can support product acclimation. And a strong embedded engineer becomes even more useful when the platform reduces deployment friction and leaves room to learn the current tools. The market tells us something important about how to hire for this space. Scarcity should push teams toward transferable skills, clear communication, and people who can bridge disciplines. Direct edge AI experience is still thin because the field is young. The better strategy is to look for people who can cover real responsibilities, learn quickly, and avoid waiting for a unicorn. That should be encouraging for a learner. A strong adjacent specialty, curiosity about the other pieces, and enough practical fluency to work across model, signal, and device can get you into real edge AI work sooner than people expect. The hiring core is not a rare all-in-one expert. It is a team that can cover applied ML, DSP, and embedded engineering well enough to move a product forward. When those three perspectives are present, the team can handle problem framing, sensor understanding, and on-device integration. That combination is enough to make real progress, even when direct edge AI experience is hard to find. Edge AI hiring depends on finding people who can connect models, hardware, and real-world constraints. The main challenge is matching the work to transferable skills when exact edge AI experience is still rare. Perfect titles matter less than the mix of abilities underneath them. The stronger question is whether someone can cover the parts of the system that actually determine whether the product works. A lot of capable candidates have built pieces of the stack without calling it edge AI. The useful search is for people who understand models, constrained hardware, and the bridge between sensor data and deployment. That changes the hiring conversation from credentials to coverage. Some gaps can be closed quickly with good tooling and training, while others need experience already in the team. Two lanes carry most edge AI work, building the model side and making it run on device. Keeping both in view prevents the team from overvaluing one half of the problem. Algorithm development is about making the model useful in the first place, from data choices to evaluation. Embedded engineering is about making that model survive on real hardware with limits on power, memory, latency, and interfaces. Both sides have to be present, even if different people own them. A strong model with no device path never ships, and a fast device with the wrong model only ships the wrong answer faster. The first hire often needs to turn an ambiguous problem into something shippable. Applied ML experience usually maps better to that kind of delivery pressure than research experience alone. Applied practitioners tend to be comfortable with imperfect data, trade-offs, and the gap between notebook results and a working system. That makes them valuable when the job is not just modeling, but getting something to survive contact with users. Academic researchers can be excellent when the technical challenge is novel or unusually hard. They may need more time on product constraints and software workflow, though, so the fit depends on how much ramp up the team can afford. A resume full of papers does not automatically solve a delivery problem. The better fit is often the person who has already handled noisy data, release pressure, and practical debugging. A strong academic profile can be impressive, but the daily work may be very different from research. For a small team shipping a device, the safer choice is often the person who knows how to keep a project moving under real constraints. Sensor-heavy edge AI creates a very specific hiring advantage for people with signal processing backgrounds. They already think in the language of noisy inputs, which is exactly where many ML teams struggle. Clean datasets are not the same as vibration streams, audio feeds, or drifting calibration signals. DSP experience helps because it prepares people for sampling rates, aliasing, missing readings, and messy physical data. DSP engineers already reason about the shape and trustworthiness of the input before they judge the model. That habit transfers directly to domains like audio, vibration, radar, wearables, and industrial monitoring. The overlap is bigger than it first looks. Both fields demand careful feature thinking and a disciplined view of what the system can safely infer from the data. A DSP engineer can often move into embedded ML without a full career reset. The useful transition is from shaping signals to helping connect those signals to model outputs and device deployment. That path usually begins with feature work and gradually expands into quantization and conversion for hardware. The goal is effectiveness at the interface, not turning the engineer into a research scientist. Embedded engineers do not need to become theorists, but they do need enough ML literacy to support deployment. That literacy helps them debug problems that only appear once the model reaches the device. They need to understand the model's expected input, the effect of pre-processing, and how to check whether a converted model still behaves correctly. That is the practical knowledge that keeps deployment work from turning into guesswork. Edge systems frequently combine neural models with feature pipelines, lightweight classifiers, or other classical logic. A strong embedded engineer can learn that tooling, especially when the platform handles much of the conversion and optimization work. When ML support is thin, the embedded engineer still needs a clear path for diagnosing failure. The key is to isolate whether the problem starts in pre-processing, conversion, tensor shapes, or a hardware limit. They do not need to redesign the architecture from scratch. They need enough tooling to test hypotheses quickly and enough literacy to ask whether the fault is in the data path, the model translation, or the runtime itself. Small teams rarely get one person per function, so overlap is normal. The important part is that overlap still leaves the team with enough breadth to cover the full system. One person may cover both data science and deployment support, while another handles embedded work and test automation. That arrangement works well as long as nobody assumes a single title removes the need for different kinds of expertise. A practical staffing plan looks for complementary coverage across the team. Applied ML, DSP fluency, and embedded competence can combine into a workable system even when no one has years of explicit edge AI experience. The market is best treated as adjacent talent territory, not a hunt for rare specialists. That perspective changes both recruiting and the way teams think about their tools. The advantage comes from people who can reason about the problem, understand the data source, and work close to the device. Those skills travel well across edge AI roles. Good platforms do not replace expertise, but they lower the amount of niche knowledge a team must bring on day one. When data handling, optimization, deployment, and collaboration are bundled well, a small team can do far more than its headcount suggests. The staffing pattern becomes clearer once the problem is framed correctly. Edge AI hiring works best when you look for people who can frame problems, understand sensors, and operate near the hardware. Applied ML, DSP, and embedded engineering are the three most useful anchors, especially in small teams where roles overlap. Strong platforms then shorten the path from adjacent experience to a working product. Edge AI learning comes down to choosing the right depth for the goal in front of you. The difference between shipping a product and pushing the field forward shapes what you study first and what you can safely leave for later. The practical rule is to match your learning to your milestone. Product work asks for enough understanding to build and validate. Research work asks for enough depth to advance methods and science. Those two paths reward different habits. One path favors fast validation and delivery, while the other favors careful exploration, experimentation, and deeper technical study. For product delivery, total mastery is the wrong target. Edge AI reaches across sensors, data, models, deployment, power, and user context, So waiting to know everything usually slows the prototype before it even starts. Just-in-time theory keeps the learning tied to a real build step, so the concepts arrive when they can actually be used. Theory helps with trade-offs and failure modes, and practice tests those ideas against noisy inputs, memory limits, weak connectivity, and power constraints. A better pattern is to define the next milestone and learn only the minimum useful material for that move. If the next step is field data, study sensors and labeling. If it is deployment, study runtime limits and memory footprint. The useful shift is from collecting information to producing the first working version. Once the goal becomes concrete, the study plan gets smaller, sharper, and easier to act on. That question breaks the habit of postponing the prototype. It turns broad curiosity into a narrow build target, and the learning starts serving the system instead of replacing it. That same pattern shows up in teams. People do not need to be perfect all-rounders. They need to cover the problem together, with each person contributing a different piece of the stack. That is why hiring often values someone who can deliver now and grow into the gaps. The best candidate is often the one who learns quickly, collaborates well, and can cross boundaries between data, software, and hardware. Broad fields punish random wandering, so curated resources matter. A small set of good references can shorten the path to a credible first attempt far more than scattered searching can. The best materials connect embedded machine learning, signal processing, and applied machine learning in one place. They help you see how the pieces fit and spare you weeks of detours. Those references should support the next stage, not become a permanent syllabus. A course, a book, a repository, and a practical community channel can be enough when each one matches the current milestone. Tooling often becomes the next bottleneck after the basic theory is in place. Edge AI is learned through a workflow, so the question is how quickly you can move from raw data to a tested system on real hardware. The workflow spans collection, cleaning, training, optimization, deployment, and testing. Each step has constraints, and the device itself is usually the hardest place to satisfy them all at once. End-to-end platforms help because they bundle several of those steps into one environment. That does not remove the hard parts, but cuts toolchain friction and gets beginners and small teams to a first result sooner. That order matters because a working system gives the low-level details a place to stick. After a first pass, runtimes, compiler flags, and board-level debugging tools make much more sense. A small team succeeds by distributing expertise well enough to avoid blind spots. The point is not universal mastery. The point is coverage across the roles that matter most. One person can judge the domain problem, another can handle collection and labeling, another can shape the model path, and another can manage device integration. When those roles are covered, the team can move with confidence even without a single expert in every area. That is the practical rule beneath both learning and hiring. Learn just enough to advance. Use the right resources to avoid detours, and let teammates and platforms cover the gaps until the first version exists. The final habit is to keep moving without pretending you need complete knowledge first. Depth can come later, after the system exists and the missing pieces become visible. Start with curated resources. Use a platform when it reduces complexity, and go lower level only where the project demands it. The goal is forward motion that turns curiosity into a working edge AI system. Edge AI learning has two main paths: building useful systems quickly or going deeper into the theory that shapes better judgment. The value here is knowing which kind of depth fits your role and your next decision. Practical learning and theoretical learning both make sense, but they serve different needs. One gets you moving sooner, while the other helps you understand the field well enough to contribute with confidence. For many learners, the first choice is whether the goal is immediate usefulness or deeper understanding. The mistake is thinking one path is inferior or waiting until you know everything before starting at all. A product builder needs speed and efficiency, while a researcher or toolmaker needs more theory to guide judgment. The right amount of learning depends on what responsibility you carry and what decisions you need to make. Trying to master the whole stack at once turns learning into a stall. Minimum viable expertise is enough if it helps you move the prototype forward, make the next decision, or ask a specialist the right question. Progress matters more than completeness at the start. In a field this broad, the fastest way to learn is to build, run into a real constraint, and then study the theory that explains it. Total mastery first is usually too slow. A build step exposes the real problems, and those problems make the technical ideas easier to understand because they now have a concrete purpose. When the goal is to ship or prototype, structured hands-on material is often the better choice. It gives you an order of operations for implementation, integration, and debugging instead of making you assemble everything from scratch. A team usually learns best by starting with the smallest useful version of the system. Once a prototype exists, questions about features, noise, compression, and hardware become real engineering problems instead of abstract topics. A working prototype gives theory something to attach to. Before that, technical ideas can feel disconnected. After that, they become tools for diagnosis and refinement. Edge AI work is usually shared work, so learning can be divided across people. Different roles need different depth, and a team gets farther by combining those strengths than by demanding one expert who covers everything. One person can focus on model behavior, another on data quality, another on device integration, and another on deployment. Those responsibilities overlap, but they are not the same job, even when a small team wears multiple hats. That division helps catch mistakes that one person might miss. Field experience, domain knowledge, and stakeholder perspective all shape whether the system will work well outside the lab. Hiring often favors people who can learn quickly and work across boundaries. Direct, edge AI experience helps, but the stronger signal is whether someone can communicate clearly and contribute inside a mixed technical team. The choice of resource should match the goal. If the job is to produce something workable, practical material helps first. If the job is to explain behavior and sharpen judgment, theory becomes more important. Practical resources reduce friction by giving you a path through the work. They're useful when you need to answer immediate questions like what to try first, what to test next, and what to ignore for now. Theory pays off when you need to understand why a model behaves a certain way or why a deployment constraint changes the design. It is not a bad starting point in itself, but it is often inefficient when the first task is simply to get something working. The best sequence is to take a small working step, then use theory to improve the next one. That keeps learning tied to decisions instead of letting it drift into abstraction. Once momentum matters, the tooling choice changes. A platform can bundle the hard pieces and help a learner or small team reach a credible prototype without spending all the early time on setup. A platform-assisted path can reduce setup risk because it covers data handling, training, optimization, deployment, and collaboration in one place. That makes it easier to reach a useful first version before building a custom toolchain. Starting with a custom stack too early can waste time when the real task is still problem validation. A platform gives the Riverwatch Node team a repeatable workflow while they learn what the system needs in practice. That convenience does not remove engineering judgment. It buys time and lowers complexity, and later the team can decide where deeper control is worth the extra effort. Starting small is not a sign of weakness. It is a disciplined way to match the learning path to the role, the problem, and the next useful result. A new learner does not need to be complete on day one. Learn enough theory to understand the problem, use practical tools to build, lean on teammates for the rest, and use a platform when it shortens the path to a first result. The goal is not to delay rigor. It is to focus it where it matters. Study selectively, build deliberately, and let the next working version show what deserves deeper learning. Software engineering is the part of edge AI that makes the whole effort workable. Before a model ever reaches a device, a stack of choices has already decided whether the team can build, test, and ship it at all. A project usually fails long before accuracy becomes the problem. The operating system, language, dependencies, and compute setup all affect whether the team can even keep making progress. The operating system matters at two different points: when you build the system and when you run it on the device. Those are related, but the constraints are not the same. On the development side, the OS affects drivers, package managers, shells, and debugging tools. On the deployment side, it controls what can actually run on the target hardware and how much room the runtime has to breathe. That is why mixed environments are common. One engineer may work where experimentation is easiest, while another works where the board tools and vendor support are strongest. The right choice depends on the job at hand, not on loyalty to one machine. Language choice also splits along the same line. One language is usually for fast ideas and exploration, while another is used when the code has to meet strict limits on a real device. Python fits the early part of the workflow because it is fast to write and easy to change. That makes it ideal for model experiments, data work, and the surrounding scripts that hold a pipeline together. C++ becomes important when memory, latency, and hardware integration start to matter. The code that talks to sensors and keeps timing predictable often needs that tighter control. That split is easy to underestimate. Python helps you discover what might work, but C++ is often where the idea has to prove it can survive the real product constraints. Once reliability matters, manual steps stop scaling. Automation turns a fragile sequence of actions into a workflow the team can repeat and trust. Scripts matter because edge AI work has many handoff points, converting a model, flashing a board, running checks, and collecting logs. Each one is a place where a manual mistake can creep in. It also protects the result from human inconsistency. If the same script produces the same steps every time, yesterday's outcome is much easier to reproduce today. Dependencies become a hidden source of failure when many tool chains meet in one project. A team can lose days to a problem that has nothing to do with the model itself. Machine learning libraries, device drivers, compiler versions, and embedded runtimes often pull in conflicting requirements. That makes version management part of the engineering work, not an afterthought. A model may train fine and then fail later because the environment changed underneath it. When that happens, the issue is usually compatibility, not intelligence or accuracy. Early end-to-end testing is the safest response. If training, conversion, runtime, and target OS disagree, finding that mismatch early saves far more time than discovering it after the device is finished. Containers help when incompatible tool chains need to live on the same workstation. They do not erase complexity, but they keep one environment from breaking another. A container can hold one build environment, while another container holds model development tools. That separation is useful because each stack can keep its own dependencies without interfering with the other. That also makes collaboration cleaner. The team shares models, logs, and artifacts through the pipeline, instead of trying to duplicate everyone's local setup by hand. A small team usually survives by separating responsibilities without separating the project. The workflow stays organized when each role has a clear environment and a shared path for artifacts. In a practical team, one person may train on Linux while another integrates the board on Windows. Containers keep those tool chains isolated, and the shared pipeline keeps the whole effort moving as one system. That arrangement is common because real projects are messy. There is usually no single clean setup that fits every role, every tool, and every constraint at once. Some tasks are simply too heavy for a local machine. At that point, remote compute stops being a luxury and becomes part of the design. Training runs, large experiments, and dataset handling can exhaust storage and time on a laptop or office workstation. Those jobs need a stronger compute plan. Cloud resources are often the practical answer for that capacity. They handle the heavy jobs, while local machines stay focused on editing, debugging, and device-side testing. That matches the nature of edge AI itself. Part of the work happens in the cloud, part happens during development, and part lands on the device at the edge, so the software stack should follow that distribution. These habits matter beyond one project or one role. They're the kinds of engineering skills that make a person useful on real teams. Hiring teams look for people who can move comfortably across environments, control dependencies, and automate repetitive work. They also want engineers who can make results reproducible instead of depending on luck and memory. The best engineers are not always the ones with the cleanest setup. Often, they're the ones who can keep a complicated stack stable while the rest of the system keeps changing. The bigger lesson is that success comes from managing the stack, not just choosing a model or device. The software layer is what lets the hardware and the algorithm actually work together. Software engineering choices shape whether an edge AI system is buildable at all. The focus here is on how teams coordinate tools, environments, and deployment so the prototype can actually become a working device. A tool choice affects multiple people, multiple machines, and multiple stages of the pipeline. A setup that works for one developer but breaks the handoff to deployment creates fragility, even if the individual pieces look fine on their own. The first useful distinction is between where the model is built and where it runs. Keeping those roles separate makes it easier to understand why one machine is great for experimentation while another must be built for constraints. A development setup is built for speed of thinking, notebooks, plotting, package installs, and quick experiments. The target system has a different job, with tight limits on memory, power, and library support. So the same code often needs to be simplified or adapted before it can run there. Operating system matters because it changes what the team can do easily. Linux or Mac OS often fit scientific Python and automation work well, while embedded workflows may still depend on Windows-specific vendor tools, drivers, or flashing utilities. Different specialists can absolutely work in different environments, and that is normal. The important part is a clean interface between them. Version control, agreed file formats, documented build steps, and a handoff that does not depend on tribal knowledge. Language choice usually follows the job at hand. Python is often the best starting point for exploration, while C++ becomes important when a model has to live inside tight hardware limits. Python gives teams mature libraries for data work, visualization, and machine learning, so ideas can be tested quickly. That short feedback loop matters when pre-processing, model structure, or error analysis still needs to be explored. C++ matters when latency, memory use, and predictable behavior are part of the design target. On small devices, engineers often need direct control over how code interacts with the runtime and the hardware itself. Scripting languages sit between experimentation and deployment by removing repetitive manual work. They're the glue that keeps build, test, packaging, flashing, and logging tasks consistent instead of error-prone. Once teams combine ML tooling with embedded tooling, version mismatches become a major source of failure. The next point is why reproducibility has to be treated as part of engineering, not as an afterthought. A model can train cleanly and still fail later if the framework, compiler, or library versions do not line up with the target workflow. ML stacks and embedded stacks often pull in different dependencies, so what looks like one project can behave like two incompatible systems. Knowing exactly what ran, where it ran, and with which versions is what makes results reproducible. Without that discipline, teams waste time chasing environment problems that look like model bugs. Containers help by separating one tool chain from another so they do not interfere. That separation turns many hidden conflicts into explicit setups that can be recreated later instead of guessed from memory. That separation is useful when one engineer trains on Linux and another packages from a Windows-based workflow, because the same artifact can still be validated in a controlled way. It also makes handoff easier, since each specialist can work in a familiar environment without breaking the rest of the pipeline. Some parts of the workflow outgrow a single local machine. The issue now is how to use remote compute and orchestration when the data, training time, or deployment load becomes too large for a laptop. Distributed computing becomes useful when there are too many artifacts, too much data, or too many repeated steps for one machine to handle well. In Edge AI, that can cover data preparation, training, evaluation, and repeated deployment tests across many targets. Cloud resources are often the easiest way to get extra capacity without buying hardware that sits idle. They're especially helpful for short bursts of training, large temporary datasets, or backend services that support devices after deployment. The goal is not to move everything to the cloud. The goal is to use remote compute, storage, and orchestration where they remove friction and keep the local machine focused on interactive work. Hiring signals in Edge AI usually come from how well someone works across layers of the stack. The ability to keep environments reproducible and the pipeline steady often matters as much as knowing the model itself. Employers want people who can move between machine learning, embedded work, and deployment because the hardest problems appear at the seams. A person who can automate builds and tests, manage environments cleanly, and reproduce results is much easier to trust than someone who only has notebook experience. Smaller teams rarely have a separate specialist for every part of the stack. That means people need enough overlap in skills to keep the pipeline moving and understand where one area depends on another. The practical rule is to pick tools that let specialists work differently without creating chaos. When the stack keeps dependencies under control and makes the path from prototype to device repeatable, the whole system becomes much easier to ship. A simple rule helps judge any tool or workflow. It has to serve both experimentation and deployment. The final point makes that trade-off explicit. A tool that helps you experiment but blocks deployment is only half a solution. A tool that runs on the device but cannot be reproduced by the team is also incomplete. The right stack supports different jobs while still producing one coherent system. Working with data at the edge starts with a simple question. Can the system collect useful readings in the real world and keep them trustworthy? That problem shapes every later design choice, from storage to syncing to training. Riverwatch Node has to solve the messy part first, because the value of the project depends on usable field data. If the data never survives the edge environment, the rest of the AI pipeline never gets a solid foundation. A remote monitor lives in conditions that cloud systems rarely face. Sensors can be cheap and noisy, power can be limited, and network access may disappear for long periods. So the workflow has to be designed for failure and delay from the start. That changes the order of priorities. First, you need a way to capture readings where the device lives, protect them when the connection drops, and organize them so they can become training data later. Before the final hardware is ready, a team still needs real observations from a field. The first job is getting enough data to test the sensors, the sampling plan, and the site conditions. A data logger is a fast way to begin because it records sensor values with very little setup. That lets the team learn early whether the signals are stable enough and frequent enough to be worth modeling. Early logs often reveal problems that would be expensive to discover later, like drift in humid conditions or missed events from the wrong sampling rate. That makes the logger a bridge from a rough idea to a deployment that can actually support model work. Network access has to be treated as uncertain, not assumed. Once that is true, both the capture system and the data pipeline need to work through interruptions instead of depending on constant connectivity. A remote site may only connect sometimes or not at all. That means the system has to keep collecting locally and remain useful even when uploading is delayed. A mobile broadband modem can move data without manual retrieval, but it introduces new limits of its own. Coverage, cost, and power draw all become part of the design, so it helps in some deployments and fails in others. Satellite links extend reach, but they do not remove the basic problem of intermittent transfer. The safer pattern is local storage first, synchronization when a network appears, and a design that expects gaps. Once devices are deployed, the operational challenge becomes keeping them visible and reachable. Device management tools help connect the physical fleet to the data workflow without forcing the team to build everything by hand. These platforms give teams a way to inspect status, trigger synchronization, and work with many devices at once. They do not replace embedded design, but they remove a lot of custom glue code around collection and monitoring. The real benefit is operational clarity. When inventory is clean and access paths are simpler, data collection is much less likely to collapse into manual checking across every site. For edge datasets, preservation matters more than fancy querying. The first goal is to keep raw observations safe and recoverable, because analysis can only happen after the data is intact. A batch-oriented workflow does not need a heavy relational database as its starting point. File system storage is often better because it is easier to inspect, move, and process when the focus is raw signal data. Riverwatch Node can keep sensor records on local flash or removable media and send them later when a connection returns. That gives the team a storage method that is simple to back up and easy to debug when hardware fails. A strong pattern is to separate the measurements from the descriptive details. The readings stay compact and efficient, while the metadata records the context needed to interpret them later, like calibration, location, and sampling rate. After collection comes transformation. The pipeline turns field logs into something a model can actually use, so the data quality work becomes part of model development rather than an afterthought. That process usually starts by cleaning corrupt samples, filtering obvious noise, combining multiple sensor streams, and reshaping the result into a training-friendly format. Each step reduces chaos and makes the dataset more reliable. The work is often delayed and irregular, so the pipeline has to accept incomplete uploads and missing intervals without breaking. Keeping the raw original data unchanged is important because later checks may depend on revisiting those first assumptions. For this kind of work, flexibility matters more than database complexity. Tools that read files well, manipulate arrays, plot trends, and support quick signal analysis are usually the fastest path to a usable dataset. The same skills that make a field deployment succeed also matter to employers. Teams need people who can move from sensor collection to clean data organization without relying on ideal lab conditions. Someone who can start with a logger, survive weak connectivity, structure files cleanly, and prepare training data is solving real project risk. That combination is useful because these problems repeat across deployed systems. Riverwatch Node succeeds through disciplined data handling, not through a fancy storage stack. The team can collect in the field, preserve the data safely, separate values from metadata, and keep the batch pipeline understandable even when the site is remote. That is the discipline to keep in mind. Edge AI usually rewards practical capture and tidy structure, not cloud-style assumptions or unnecessary database complexity. When the data path is solid, the modeling work becomes much easier to trust. Data handling is the first constraint that shapes an edge AI system. If collection, storage, and preparation are weak, model choice and deployment details cannot rescue the project. A team has to capture useful sensor readings in places where connectivity may be weak or missing, then keep those readings intact long enough to train on them. Riverwatch Node makes that problem concrete, because the first question is not model design, but how to collect data from the field at all. The collection system has to be shaped by the site itself. Remote locations, moving machines, and constrained buildings all change what reliable capture looks like. Edge data rarely comes from a controlled lab setting. It may need local logging, buffering for long periods, and storage that survives outages, temperature changes, and reboots without losing the record. That is why early tools are often picked for durability rather than polish. A simple data logger can start collecting usable samples right away, even if the team retrieves the files manually for a while. Wireless transmission works only when coverage, power, and cost all line up. In a remote deployment, local logging can be the better choice because it avoids depending on a link that may be expensive, power-hungry, or unreliable. When hardware can already communicate, a management platform can reduce a lot of custom work. It becomes useful for registration, health checks, secure messaging, and fleet coordination. That middle ground matters because embedded devices with real connectivity can be easier to manage through platform libraries or APIs. The platform handles the routine coordination, so the team does not have to build every control path from scratch. For a one-off prototype, or for a very isolated site, a simpler local logger may still be the smarter first step. The tool should match the deployment reality, not the other way around. Sensor datasets usually move through batch workflows, not interactive application queries. That means storage should support collection, cleaning, and reformatting with as little friction as possible. A database can feel like the obvious choice, but Edge AI data behaves differently from typical app data. When the job is to process blocks of readings, a file system first approach is often the cleaner fit. Simple files are easy to create on device, archive later, and hand off to a pipeline. Heavy relational tools are usually optimized for joins and transactions, not for large sensor arrays or waveform dumps. A manifest can carry the metadata that gives the readings meaning, sensor type, sampling rate, device ID, location, calibration notes, and label references. Keeping that information separate keeps the data portable and avoids rewriting large files just to update descriptions. Compact binary files often suit repeated training pipelines better than database schemas do. They move faster, waste less space, and avoid forcing the measurements into a structure that distorts them. Once the data exists, the pipeline becomes the part that turns raw readings into something usable. It has to clean, align, combine, and split the data before any model work can begin. A good pipeline removes corrupted samples, normalizes timestamps, joins contexts like location or operating mode, and prepares training and validation batches. That process matters because model quality depends on consistent input, not just on more data. For Riverwatch Node, the pipeline may take raw environmental readings, drop malformed intervals, and attach deployment metadata before writing out files for model development. The goal is a process that is predictable, inspectable, and fast enough for the amount of data coming from the field. When the pipeline fits the data, experiments stay repeatable, and the team does not have to recollect everything for each new idea. For sensor-heavy work, that usually means file-oriented ingestion, batch transforms, compact binary storage, and lightweight metadata instead of generic database assumptions. This turns into a job skill, not just a technical preference. People who understand weak connectivity, file structure, and batch preparation can lower project risk in a way that general database knowledge alone often cannot. In Edge AI, practical fluency means knowing how to survive poor links, organize sensor data cleanly, and prepare batches for training. That combination is valuable on any team size because it keeps the data path from becoming a bottleneck. That is the working discipline for sensor-heavy systems. If Riverwatch Node can collect data well, keep storage lean, and process batches without friction, it has already solved one of the hardest parts of the project. Algorithm development for Edge AI is a fast loop of data inspection, hypothesis, testing, and refinement, with device limits shaping every step. The point here is to understand why the workflow has to be both exploratory and disciplined. That loop matters because the first idea is rarely correct in its original form. On edge devices, each pass also has to respect memory, latency, and what the hardware can actually run, so the method and the constraints are tied together. No single package covers the whole process well. The practical workflow combines array tools, table tools, scientific transforms, visualization, notebooks, training frameworks, compression tools, tracking, and pipeline automation so the experiment can become a repeatable system. The first job is turning raw measurements into data you can reason about. That means moving from unstructured sensor values to a form that can be inspected, cleaned, and compared with confidence. Number PY gives fast array operations. Pandas helps organize timestamps and labels. And SciPy adds filtering, interpolation, and resampling. Those pieces matter because edge data often arrives messy, sparse, or uneven, and the first transformation stage determines whether later modeling has a chance. A simple inspection pass often exposes problems in structure that a model would hide. One channel may be stuck, another may drift, and a third may line up with the event you care about. So a small visual check can save a lot of wasted training. Plots are diagnostic tools, not decoration. Histograms, scatter plots, and time series views reveal stuck sensors, operating modes, missing intervals, and deployment glitches, while notebooks keep the code, plots, and reasoning in one place, so the experiment stays traceable. A small, concrete workflow is often the fastest path to a useful baseline. The goal is to move from raw sensor data to an early model without losing sight of what the data is actually doing. A practical first pass starts with loading the data, checking the columns, sorting by time, and comparing summary statistics. Then the plots get annotated with what looks meaningful, what looks broken, and what needs more checking, which turns a notebook into a working lab record. A baseline model is for checking whether the learning problem is even well-formed. If a small network cannot beat a trivial comparison, the issue is usually in the data, the labels, or the feature design rather than in model sophistication. The important idea in this model is not depth, but structure. The dense layers create a small baseline for tabular sensor features. The sigmoid output matches binary classification, and the validation set checks whether the model generalizes instead of just memorizing the training data. That setup is deliberately simple because the lesson is about process. A small experiment makes it easier to see whether the inputs are sensible, whether the labels line up, and whether the results are comparable from run to run. Framework choice matters more when deployment is part of the plan. The target hardware should influence the choice early, because training convenience alone is not enough when the final model has to run on constrained devices. TensorFlow and PyTorch are both important, but they connect to edge deployment differently. If on-device compatibility is part of the goal, the framework decision should favor the path that makes conversion and runtime support easier later. Practicality matters more than ideology here. A good choice is the one that aligns with the team's experience, the form of the data, and the runtime constraints of the device, because that combination determines whether the model survives beyond the notebook. Once a first model exists, the real risk is losing control of the experiment history. The next tools are the ones that make changes measurable, results reproducible, and the workflow stable enough to repeat. If layers, learning rates, and pre-processing steps change without records, the result becomes hard to trust. Optimization, tracking, and automation exist to keep the search organized so you can tell which change caused which outcome. On edge systems, cost can mean compute, memory, latency, or manual effort. Compression methods, such as pruning and quantization, matter because the model has to satisfy the runtime limits of the target device, not just the training environment. Reproducibility starts with disciplined logging. When the data version, feature set, hyperparameters, random seed, and metrics are captured, the run can be recreated and explained instead of merely remembered. AutoML can reduce manual trial and error, especially when comparing feature sets or tuning a constrained model family. It still depends on clean data and careful evaluation, and it never removes the need to think about what the device can actually execute. Pipeline thinking links all the stages together so the project stays sustainable. A change in field data, pre-processing, or runtime support can affect every later stage, which is why these steps have to be managed as one life cycle rather than separate tasks. Automation pays off because it makes the work auditable and easier to hand off. When the process is scripted, a fresh dataset or a changed field format does not force the team to rebuild the whole experiment by memory. Employers often look for people who can move between analysis, model building, and deployment-aware decisions without friction. The strongest signal is usually not a benchmark claim, but the ability to make the workflow reliable and explainable. That mix of skills is valuable because real projects break at the boundaries between steps. Familiarity with pandas, notebooks, TensorFlow, and tracking tools often matters more than winning arguments about which framework is fashionable. Reliability shows up in the small habits. Easy inspection, save parameters, separate training scripts once the experiment stabilizes, and data handling that accepts new field captures without manual cleanup. Those habits make the system usable after the first prototype is finished. That habit turns edge AI into engineering instead of guesswork. The work starts with data, moves through a small testable model, and ends with reproducible steps that can survive a real device and a changing field environment. Algorithm development is where an edge AI idea turns into runnable work, and the first challenge is usually building a workflow that lets the team test ideas quickly without losing control of the results. The early decisions are less about polished model design and more about the tools, files, and habits that make experimentation fast and traceable. When that foundation is clumsy, even simple tasks like inspecting data or comparing runs become slow and hard to trust. The first pass usually starts with raw sensor data and ends with a baseline you can actually evaluate. That means cleaning, aligning, and checking the signal before anyone spends time on a fancier model. A practical first workflow reads field data, lines up timestamps, handles missing samples, and separates obvious noise from useful variation. The code is doing the same job a lab notebook used to do by hand, turning observations into something you can reason about. A small slice of prototype data is often enough to reveal whether the idea has a real signal in it. Domain experts matter here because they can point out which anomalies are expected and which parts of the data would make a model misleading. NumPy and pandas handle the arrays, tables, cleanup, and feature work that make the data usable. Matplotlib and Seaborn then show the structure hiding inside it, which is important because visualization often reveals sensor behavior before the model does. Notebooks are valuable when the team is still testing ideas because they keep code, notes, outputs, and plots together. That makes the reasoning visible while the approach is still changing. A notebook lets one cell load the data, the next inspect a sample, and another compute a feature right beside its result. That tight loop is useful because it shows not just what happened, but why the team trusted the step. That kind of visibility supports reproducible iteration, especially when several pre-processing choices or feature sets need to be compared. Once the approach settles, the useful logic belongs in a script or pipeline stage so it can run again without manual work. Exploration can be messy because the team is still trying ideas, but the later script should make the same inputs, transformations, and metrics happen the same way every time. That shift is what makes a result trustworthy instead of just interesting once. A minimal training loop is enough to show the structure of model development without pretending deployment is solved. The value is in seeing the pattern clearly. Define, compile, train, and evaluate. A simple CARES example makes the workflow concrete. The model is defined first, then compiled with a loss and optimizer, then fit on training data, and finally checked on held-out data. That sequence keeps the roles of each step separate, which helps avoid confusion between learning the model and judging it. The sequential model starts with an input shape, then one hidden dense layer, then an output layer size to the number of classes. Compilation sets the optimizer, loss, and metric, and the fit call trains on the training set while watching validation data, so the team can see whether learning is generalizing before the final evaluation on the test set. That tiny loop teaches good habits immediately. Model setup stays separate from training, evaluation stays explicit, and validation performance matters as much as training performance. The history object is useful too, because it can later show learning curves and reveal overfitting or underfitting. Edge-aware implementation means thinking ahead about reproduction, export, and later optimization while the baseline is still simple. The code should be organized so those constraints can be handled without rebuilding the whole project later. Employers value engineers who can move comfortably between code, data inspection, and discipline experiments. The practical skill is not loyalty to one framework. It is getting from data to evidence quickly and repeatably. Someone who can use notebooks, Python ML workflows, and Keras-style iteration is often useful much sooner than someone who only knows one narrow tool. That range matters because edge work depends on turning messy data into evidence that can be trusted. Edge projects rarely stay still, so the engineer has to compare variants systematically and keep track of what changed. The people who keep those projects moving are the ones who can document the work and hand off code that others can rerun. For Riverwatch Node, the work begins with a notebook, a small batch of sensor data, and a baseline model that can be compared against later ideas. That is real engineering already, because it turns exploratory thinking into something the team can inspect, reproduce, and adapt for the device. Early Edge AI is about using the right tools to make experiments understandable and repeatable, not just to make a model run. Notebooks help the team think. The numerical stack helps shape the data. A simple Keras workflow establishes a baseline, and disciplined implementation habits keep the path open for what comes next. Running a model on a device is not just a modeling problem. It is a deployment problem. The real question is whether the runtime, memory limits, and hardware support line up with the model you trained. A model can look strong in a notebook and still fail on the device if the execution path does not fit the hardware. The gap between training and deployment is where edge projects often stall. Training lives in a flexible environment where it is easy to experiment and revise assumptions. Deployment lives in a narrower world where latency, memory, and power decide whether the model is actually usable. The first practical check is whether the target has optimized kernels for the operations the model needs. That determines whether the hardware can turn a correct model into a fast one. Matrix math, signal processing, and neural network layers all depend on kernels that do the heavy lifting efficiently. Without them, even a valid model can spend too long in generic computation. A device with good DSP and math support can make a modest model feel quick, while a weaker target can struggle with something small. Often the bottleneck is not the model itself, but the missing kernel support underneath it. There are several ways to get from a save model to running code, and each one balances portability against efficiency differently. The choice changes how much work the device does at runtime. Every deployment path gives up something. The useful habit is to ask which trade-off matters most for the device and the product goal. An interpreter loads the model and steps through it directly, which makes the workflow simple and familiar. The cost is extra overhead, so convenience usually comes before raw speed. Code generation moves the work earlier, producing code tailored to the model and the target. That usually improves efficiency, but the result is tied more closely to that specific deployment path. A compiler that understands the target can emit low-level code the device executes directly while applying target-specific optimizations. In that setup, the model is being adapted to the silicon instead of asking the silicon to adapt later. A virtual machine can make deployment more consistent across a family of devices because the environment stays the same. The trade-off is that abstraction can hide performance costs, which matters when every millisecond counts. HDL-based synthesis moves beyond software and turns the model, or part of it, into hardware logic. That can be extremely efficient, but it also shifts the work into hardware design and verification, which is a much harder path. Some accelerator chips work through special interfaces that do not look like ordinary application code. The model may be loaded into a dedicated buffer and handed off to vendor-specific hardware, which can be fast and efficient but very tied to that vendor. A team might begin with a lightweight runtime because it is the quickest route to a working prototype. If latency becomes a problem, the same model can move toward generated code or a specialized accelerator, depending on what the hardware supports. Compression sounds like a shortcut, but it only helps when the target hardware and runtime can actually exploit the compressed form. The real issue is compatibility, not just smaller files. Quantization can shrink the model and reduce arithmetic cost, but the target has to understand that numeric format. If the kernels do not match, the model may still run, but the expected speedup will not appear. Pruning removes weights and creates sparsity, but zeros alone do not guarantee faster execution. The hardware or runtime needs sparse-aware kernels. Otherwise, the model is just smaller on paper. For Riverwatch Node, the useful model is the one that maps cleanly onto the available kernels. A slightly larger model can outperform a smaller compressed one if the smaller version falls back to generic execution. The next temptation is to assume that training on the device or using federated learning should be the default. In practice, those options add complexity, so they should be chosen only when the product really needs them. Training on the edge asks for more memory, more compute, and more system complexity than inference. Most products only need reliable prediction on the device, not full model updates there. Federated learning can help in privacy-sensitive systems, but it is easy to overuse as a solution. It brings coordination, overhead, and infrastructure complexity. So the simpler question is often whether the device can just run the model well. The practical order is clear. First, fit the runtime to the hardware, then verify kernel support, then make sure compression actually helps at execution time. On-device training and federated learning belong in the special case column, not the default one. A lot of people can train a model, but far fewer can make it behave under memory pressure and latency limits on real hardware. That deployment skill is often what separates a prototype from a product that ships. The most robust path is usually the least complicated one that still matches the hardware. Prefer optimized kernels, keep the deployment path honest, and only reach for exotic options when the product constraints really demand them. On-device deployment changes what matters. Not just whether a model works, but whether it works under tight limits on memory, latency, and power. The rest of the stack has to match those limits, or the model never becomes a usable product. A model can look strong during development and still fail once it is squeezed onto a small device. The hard part is no longer experimentation. It is making the same idea survive the constraints of real hardware. Deployment involves a chain of choices: runtime, kernel support, compiler style, accelerator access, and whether compression can be executed efficiently. If any link in that chain is weak, the model may be correct in theory, but unusable in practice. The base layer comes from general-purpose math and DSP libraries. They handle the routine operations well, so teams can focus on the model instead of rewriting low-level arithmetic from scratch. These libraries provide the common pieces: filtering, convolution, matrix math, and fixed-point operations. Their real value is that they bring tested performance to tasks that show up again and again on edge devices. Edge systems often do more than inference. They clean signals, extract features, and only then hand data to a model, so efficient signal processing matters just as much as the network itself. Once the basic libraries are in place, kernel quality starts to determine whether the device can actually meet its deadlines. A better kernel can turn an almost working system into one that fits the product limits. A kernel is a concrete implementation of an operation on a specific processor. On small hardware, that difference shows up immediately in response time, memory pressure, and power draw. A desktop benchmark can hide the real problem. The target chip may not have a fast path for the operation that matters most. If the needed convolution or matrix multiply is not supported well, the model can become too slow or too expensive to ship. The deployment route changes the outcome even for the same model. A flexible interpreter gives easy testing and portability, while code generation or specialized silicon can deliver better performance if the tool chain and kernels line up with the target device. The main question now is how inference actually runs on the device. Each execution model trades flexibility, portability, and speed in a different way. There is no single best runtime path. The right choice depends on how much flexibility the team needs, how much overhead it can tolerate, and how tightly the model must fit the hardware. An interpreter runs the model step by step and is often the easiest path for early deployment. That flexibility helps when many devices are involved, but the extra abstraction costs time. Code generation moves in the opposite direction. It produces code tuned to one target, which can reduce runtime cost, but it also makes the deployment more dependent on that exact environment. Bytecode keeps some portability while giving the runtime a more structured form to execute. It is a middle ground, less raw flexibility than interpretation, but usually cleaner than carrying the full model graph around. A virtual machine adds another layer of control over the hardware. That can help with sandboxing or a stable interface, but every extra layer usually costs some performance. HDL generation goes further and pushes the computation toward hardware synthesis. The payoff can be excellent speed, but the workflow is much more hardware-centric and demands careful toolchain alignment. Some accelerators expose custom interfaces instead of standard software hooks. Those devices can be very capable, but they usually require extra engineering to fit the model, compiler, and hardware together. Compression tricks matter only when the rest of the stack can exploit them. The next question is whether the runtime and hardware actually understand the smaller model representation. Quantization and pruning can reduce size and sometimes speed things up, but they are not automatic wins. Their benefit depends on whether the execution path can make use of the change. A quantized model can still fall back to slow conversions if the device lacks matching kernels. Prune sparsity has the same problem. Zeros only help when the runtime knows how to skip them efficiently. One deployment stack may show almost no gain from compression, while another turns the same model into a real win. The difference comes from whether kernels, compilers, and hardware all support the optimized form. That is why kernel support gets checked before anyone celebrates a smaller model. An optimization only matters after the runtime can actually execute it the right way. Training on the device is a special case, and it needs a lot more caution than inference. The line between light adaptation and full training is much wider than it first appears. Adjusting a threshold or comparing embeddings can be practical on-device adaptation. Full training is different. It brings memory, compute, debugging, and coordination demands that small devices usually cannot absorb well. Before training on device, it is worth asking whether the system can infer locally and send updates elsewhere, or whether server-side adaptation would be safer. In many cases, a simpler workflow gives the same benefit with far less risk. The practical rule is to fit the runtime to the hardware, verify the kernel path before relying on performance tricks, and reserve on-device training for unusual cases. That judgment is what separates a model that looks good on paper from a system that can actually ship. Edge AI only works when software, hardware, and electronics are handled together. The main idea is that a model on a device has to survive real sensors, clocks, power, buses, and debugging limits, not just a clean training environment. A good model is only one piece of the system. Once it moves on to silicon, the real work includes power stability, sensor behavior, communication buses, and the messy physical world around the device. A beginner board gives you a smaller surface area to learn on while still forcing real embedded habits. You can practice reading inputs, driving outputs, handling timing, and watching how data moves over a serial link without getting buried in hardware complexity. The first useful skill is touching the device directly and seeing what it is doing. That means learning to inspect signals, flash firmware, and verify behavior with actual hardware tools. A debug probe lets you load and pause firmware, while serial output gives you a simple stream of logs and status messages. A multimeter confirms voltage and continuity, and scope tools reveal timing problems that software alone cannot expose. For an early prototype, the first job is to prove the chain from sensor to firmware to output pin. If the LED or GPIO does not change, a quick measurement helps separate a model problem from a wiring or firmware problem. Development boards let you test chip choices before committing to a custom design. They make it possible to compare performance, memory use, and peripheral support while the hardware is still flexible. The same model can behave very differently from board to board. A chip that looks good on paper may fail on memory, tool support, or interface availability once you run the full stack on it. Trying several kits early is cheap information. It tells you which limitation is real, which board is only failing because of tooling, and whether the design should move toward a different platform. Embedded development has its own build and deployment rhythm. The compiler, linker, flashing process, and debug tools all shape whether firmware can be loaded, recovered, and maintained reliably. A typical embedded workflow includes vendor tools, an SDK, and often Redo support. You're also dealing with architecture-specific builds, memory layout, and firmware packaging for devices that may be hard to recover if something goes wrong. The boring setup work matters because it prevents fragile prototypes. If logging disappears after boot or the flash path is unreliable, the whole system becomes hard to reproduce and even harder to debug. When real hardware is slow to access, virtual tools can keep development moving. They help shorten feedback loops, but they never replace the final check against the actual device. An emulator lets you execute device code locally instead of repeatedly flashing hardware. That saves time during development, especially when the main task is logic testing rather than physical integration. Simulation becomes useful when timing matters or when a peripheral is not available on the bench. A cycle-level model can estimate how long a path takes and whether the algorithm can meet the device's deadline. Bare metal firmware and embedded Linux solve different problems. One gives tight control over hardware, while the other gives a richer runtime with more software convenience and more operational responsibility. A microcontroller setup usually means lean code and direct hardware interaction. Embedded Linux adds easier access to familiar libraries and sometimes pre-built inference runtimes, which can reduce friction for application work. That convenience comes with extra work on security, packaging, and updates. More software layers create more room for misconfiguration and dependency drift, so the trade-off has to fit the product. A production path often starts from a vendor board rather than a fully custom design. That approach can be sensible when the product needs a capable runtime and the board ecosystem already matches the application. Embedded systems need testing that survives hardware faults and awkward restart states. The goal is to bring repeatable checks into continuous integration so failures are caught before deployment. A board may fail in ways that are hard to reproduce by hand. Automated control of power, inputs, and recovery steps makes it possible to keep testing even after the device becomes unstable. A simple test rig can feed synthetic inputs into the system and force the sensor path to run on demand. That kind of setup does not automate everything, but it makes the device testable when normal usage would be too slow or unreliable. These skills carry a lot of value because they connect code to real devices. Someone who can flash boards, read logs, inspect signals, and build regression tests can keep a project moving when pure software experience is not enough. The practical strategy is to match the tool to the question. Use a small board for fundamentals, a dev kit for hardware comparison, emulation for speed, embedded Linux when the product needs it, and hardware tests when reliability matters. Edge AI becomes real only when the model meets the device, the tools, and the physical world around it. The focus here is the engineering work that turns an algorithm into something you can program, observe, recover, and trust on hardware. A working model is only part of the story. The harder question is whether the device can be programmed, inspected, restarted after failure, and still proven correct after changes. Because source code, flashing, logging, power, and physical testing all affect the final behavior. A simple development board gives you a safe place to learn the mechanics of embedded work. I/O, timing, sensors, and basic deployment. That kind of platform removes enough toolchain complexity to build confidence before moving to more demanding hardware. The useful way to think about embedded tools is by job, not by brand. Some tools get code onto the board, some let you inspect runtime behavior, some move data in and out, and some measure what software cannot directly see. Each group solves a different layer of the problem. Flashers and bootloaders program the device. Serial consoles and debug probes expose runtime state. UART and USB bridges carry data, and instruments like oscilloscopes and logic analyzers reveal timing and signal problems that software logs will miss. That kind of physical check prevents false confidence. If the code compiled but the board is mapped differently, the wiring is wrong, or the pin never changes state, a desktop debugger will not catch it. A quick measurement on the hardware will. Development boards sit between an idea and final electronics. They let a team compare processors, test fit, and discover trade-offs early before committing to custom hardware that is expensive to change. One board may win on power, another on memory, another on software support. The point is to learn which constraint matters most for the product instead of assuming the fastest chip is automatically the best choice. A chip that looks ideal on paper can fail in practice because of heat, RAM pressure, boot time, sensor support, or toolchain friction. Early board testing exposes those limits while the architecture is still easy to change. The embedded workflow is a tighter loop than ordinary software development, and it is much more physical. Code has to fit, flash correctly, boot on real hardware, and then survive repeated testing with the actual peripherals attached. Compilation and linking shape memory layout, startup behavior, and whether the program even fits the device. After flashing, the important evidence comes from boot logs, sensor reads, and pin behavior, not from the build system alone. That is why vendor IDEs, SDKs, drivers, and flashing tools matter so much. On many microcontroller projects, C++ and a board-specific stack remain the center of the workflow, and Enritus adds discipline as well as new constraints. Before touching real boards, it helps to separate two kinds of virtual testing. One tries to behave like the target hardware closely, while the other abstracts more and gives faster answers about timing or behavior. An emulator is useful when the question is whether firmware boots, talks to peripherals, and keeps moving correctly. Once the basic logic is stable, flashing the physical board confirms that the same behavior survives real hardware. A detailed simulator can estimate latency well enough to rule out designs that will never meet a timing budget. That does not replace measurement, but it saves time by filtering out impossible paths before the board arrives. At some point, the workflow often shifts from a small microcontroller to an embedded Linux system on an SoC. The constraints change shape. More familiar software tools may return, but boot, packaging, security, and system management become part of the job. Python, DSP libraries, and containers can make development feel more comfortable, especially for software-heavy teams. The trade-off is that the system now needs build management, package management, boot configuration, and security hardening to stay reliable. A ruggedized SoC platform can speed delivery because it avoids a fully custom stack. Even so, updates, permissions, attack surface, and long-term maintainability still need careful attention because embedded Linux is different from bare metal work, not easier by default. The testing loop does not stop at software and emulation. The next step is to automate the hardware itself, so flashing, rebooting, and sensor stimulation can happen repeatedly without manual intervention. Automated hardware tests bring continuous integration into the physical world. By power cycling crash devices and driving the sensor path on demand, the team can catch failures that only appear after reboot, under load, or after long run times. People who can bridge software, electronics, and deployment constraints are immediately useful on teams that are still learning the hardware side. Knowing which tool belongs to which stage makes it much easier to move from prototype work to a product that can actually ship. The discipline of edge AI engineering is to start small, choose the right tool for each layer, and verify everything against real hardware. A model only becomes trustworthy after it survives the physical system it will live in. Edge AI depends on more than model accuracy. The hard part is coordinating data, training, device limits, deployment, and retraining so the whole pipeline stays usable. A project can fail at any handoff: data collection, labeling, feature work, optimization, or deployment. Separate tools make each step possible, but they also create friction, version mismatches, and extra work at every boundary. The question now is what that word actually means in practice. A real end-to-end platform covers the whole path from raw data to a model running and being checked on the target device. That means the same environment can ingest data, support annotation, train models, optimize them for latency or size, and test whether they fit memory and power limits. When those stages are linked, a change in one place flows into the next with much less manual repair. That connection matters because Edge AI usually spans several roles. A platform gives the domain expert, the data person, and the embedded engineer one common place to work instead of scattering decisions across separate tools. A vibration sensor team can rule out bad ideas before wasting time on them. If the platform estimates latency and memory early, model choice becomes a fit-for-device decision, not just an accuracy contest. The next idea is the feedback loop. Good platforms shorten the path between a data change, a new experiment, and a deployment result, so teams can learn faster from each run. That loop covers the whole embedded path, not just experiment tracking. A failed deployment can be traced back to pre-processing, architecture, or optimization settings, which saves a lot of time spent hunting through files and versions. For small teams, that matters because the infrastructure burden drops. Managed compute can get them to a serious prototype without building their own training stack first. So more effort goes into learning from data. Share data sets, pipelines, and model outputs let different people work in parallel without duplicating effort. They also let non-technical stakeholders review examples and failure cases, which helps confirm that the system is solving the right problem. A strong platform helps with selection, not just training. It can suggest compact architectures, warn when a device is likely to run out of memory, and search across signal processing and model options when the best answer is not obvious. A concrete example makes the difference easy to see. First, a team using a platform can test ideas against the target device early. Then the same project done by hand shows where the hidden work piles up. A startup building an occupancy detector can inspect noisy labels, test model families, and estimate device fit before deployment. That early feedback prevents the team from spending time on configurations that look good in training but fail on the hardware. A hand-built workflow forces the team to stitch together storage, notebooks, training, conversion, benchmarking, and deployment. Even if each tool is good, the integration work grows fast, and some bugs only appear after the device is already flashed. A platform is only helpful long-term if it can cooperate with other tools. Export, APIs, and mixed tool chains let a team keep flexibility instead of getting trapped inside one workflow. That balance affects hiring too. If the routine work is handled well, people can contribute through their own strengths, and a small team can still move forward without everyone being expert in every layer. A related trend appears in hardware. ML sensors show the same push towards simplification by packaging sensing and inference into a smaller interface that hides some of the integration burden. That design choice points in the same direction as an end-to-end platform. Both reduce routine integration work and present a messy chain of tasks as something more manageable for the developer. The caution is that a platform is a tool, not a destiny. Cost, openness, lock-in, and custom integration needs all matter, so the best choice depends on the team's reality and deployment constraints. The core lesson is that the best edge AI projects minimize unnecessary friction. End-to-end platforms help by making the path visible and testable, while still leaving room to step outside when the project needs something custom. End-to-end platforms matter because edge AI lives under tight hardware limits, and teams need a clear path from raw data to something that actually runs on a device. The focus here is how visual workflows, dashboards, collaboration, and interoperability make that path easier to manage. A visible workflow changes how teams reason about the work. When the full path is laid out step by step, it becomes much easier to spot where data, training, optimization, or deployment is breaking down. The contrast is between scattered work and connected work. In Edge AI, that connected view matters because the model has to survive real latency and memory constraints, not just look good in a notebook. A platform that keeps the whole chain together helps the team catch mismatch problems sooner. A model can look fine during training and still fail after quantization or on a small processor. So the earlier those limits appear in the workflow, the less wasted effort later. The important dashboard views do more than store files. They help people make decisions about model choice, device fit, and the trade-offs that shape a real deployment. A useful platform screen should guide action. It should help a team decide what kind of model to try, how close it is to the target hardware, and whether the current direction is worth continuing. When the data shape is visible, the first model choice becomes more informed. Audio, vibration, and sensor streams often point toward classifiers, anomaly detectors, or signal processing pipelines instead of a generic deep network, which helps avoid a poor starting point. That preview is useful because it turns hardware fit into something you can compare while searching for models. Instead of finding out too late that a candidate is too large or too slow, the team can watch those costs appear during the search itself. That is the real value of the dashboard. It compresses the gap between a model that seems promising and a model that can actually run on the device you plan to ship. Collaboration is not an extra feature here. A strong platform has to help different kinds of people work from the same project without losing context or version control. Small teams still need a mix of skills: data work, embedded systems, domain knowledge, and product judgment. A platform earns its place when it helps those people coordinate without each person rebuilding the whole picture from scratch. That shared workspace reduces version confusion and makes review possible for people who do not live inside notebooks. One person can inspect labels, another can judge behavior, and another can check hardware limits, all from the same project state. Cloud-managed compute raises the pace of exploration. Instead of running one experiment after another by hand, the platform can launch many runs in parallel and collect the results together, which is a major advantage for a small team. A platform should reduce friction without locking the team in. The best systems still work without side tools, so the workflow can stay flexible when the project needs something the platform does not provide directly. Those connections prevent the platform from becoming a dead end. If a team can export artifacts and plug into internal build systems, vendor tools, or custom analysis scripts, then the platform remains useful across the rest of the stack. That distinction matters because the platform should sit in the middle of the workflow, not own every decision. When outside code and tools can still flow through the project, adoption can happen gradually instead of all at once. That is why practical teams adopt them selectively. The goal is to remove hand-built plumbing and keep the project moving, not to force a complete rewrite of the existing toolchain. The choice becomes clearer when speed, shared visibility, and lower maintenance matter more than building every piece yourself. In those cases, a platform can save a lot of effort without sacrificing the technical goal. A bespoke stack sounds attractive, but it also means owning data ingestion, annotation, tracking, conversion, optimization, validation, packaging, and collaboration. For many teams, that is not elegance. It is time spent maintaining infrastructure instead of shipping a result. That is especially valuable when the team lacks deep expertise across every layer. The platform supplies much of the scaffolding, so the group can learn from real data and get to a credible prototype sooner. A custom stack can still be the right choice, but it should be chosen for a reason. If the team builds its own workflow, it should be because that control is truly needed, not because the default path was never questioned. ML sensors solve a narrower problem than full platforms. They are useful when the sensing task is well defined and the application only needs a compact inference component at the edge. That pattern is strong when a use case is narrow and the integration burden has to stay small. It gives the developer a simpler interface by hiding much of the internal machine learning work. The relationship is easy to keep straight if you separate scope. A sensor makes one edge node easier to use, while a platform helps manage the full journey from data to deployment. That is the practical lesson to hold on to. End-to-end platforms reduce risk, speed iteration, support collaboration, and keep hardware limits visible, while still leaving room to export and integrate with the rest of the toolchain.